Okay, so um, continuing on 7.4 in this unit, we are going to learn how to calculate the empirical formula of a compound. Okay, so before we do that, let's learn about what an empirical formula is. So, an empirical formula is the simplest whole number ratio of atoms in a compound. What that means is it basically tells you in your formula what is the ratio of one element to the other. That's it. Okay. So imagine that you have this compound with two carbons and six hydrogens. The empirical formula of this compound is just CH3 because this is the simplest ratio. It just tells you that in this formula you have one carbon for every three hydrogens. Okay. So the empirical formula can pretty much be the same for any compound that has this same ratio. So all it gives us is, oh, it has this many of this element to this many of the other element. Okay, so you could have, let's say, if I put a um, 3 and a 9 here, if this was C3H9, that was the formula of a compound, the empirical formula would still be CH3. Okay, so um, C3H9, because you can divide it to get CH3, and that will just tell you, oh, for every one carbon, there's three hydrogens in the compound. Same for this one. For every one carbon, there's three hydrogens. Okay, so many actual compounds can have the same empirical formula. It's the simplest whole number ratio of atoms in a compound. Okay, so there are steps you have to follow in order to determine the empirical formula of a compound. I'm going to go through them one by one and then we're going to do a couple of calculations based on those. Okay, so if you know the percent composition of a formula, um, then, I mean, if you know the percent composition of a compound, then you can calculate the formula, because if you have, let's say, 100% of a compound, you can say that the 100% is equal to 100 grams. Okay, and then the percentages just become the grams in those compounds. Okay, it'll become more clearer when we actually do a problem. Okay, what you do is then you take those grams and you convert the grams of each element to moles of each element. After you convert to moles, you divide all the mole values by the smallest mole value, and if it doesn't give you a whole number, then you have to multiply those values by a number that'll make it into a whole number. So if let's say you got a 0.5, you have to multiply it by 2 to get a whole number. If you got a 0.33, you have to multiply that by 3 to get a whole number. And if you got a 0.25, you got to multiply that by 4 to get a whole number. Okay, so you multiply all of those values by a whole number that corresponds to your fractional subscript. Okay, so all of this seems to be just information. It won't make any sense until you put it into practice. So let's do that right now. Okay, so here's your first example. It tells you to find the empirical formula for a sample of 25.9% nitrogen and 74.1% oxygen. So the earlier part of this PowerPoint, we calculated percent composition. So we're saying that you have found a compound that is made up of 25% nitrogen and 74.1% oxygen. I want to know what is the ratio of nitrogen to oxygen atoms in this compound. Okay, so it's something that we don't know yet, but we can calculate it if we follow these steps. So I made the steps from the previous slide smaller so we can do it step by step. I'm going to do the work on the right side and you can follow along. Okay, so if percent composition is known, it is known. We know it's 25.9% and 74.1%. Then a formula can be calculated because we can say that the 100% can correspond to 100 grams. That means if you have 25.9%, what you have is 25.9 grams of nitrogen. And if you have 74.1%, you have 74.1 grams of oxygen, okay, in 100 grams. Because out of 100, 25.9 is nitrogen. So 25.9 grams of nitrogen is there, and then 74.1 grams of oxygen is there. So the reason that I'm writing it like this is because of the second step, which asks you to convert the grams of each element to moles of each element. So we have to go from grams to moles. The percentages became the grams, and now we're going to go to moles of each element, which we learned how to do in the previous part of this unit. Okay, so we know the molar mass of nitrogen from the periodic table is 14.01 grams, and then we know the molar mass of oxygen, that not diatomic oxygen, just plain oxygen, is 16 grams from the periodic table. Okay, grams of nitrogen cancel out. This will be 1.85 moles of nitrogen, and then over here you're gonna have 4.63 moles of O, because grams of O and grams of O cancel out to leave you with moles. So now you have moles of nitrogen and moles of oxygen. The third step, so we've done this, we've done this. The third step tells you divide all mole values by the smallest mole value. Now, before you do that, I actually want you to write this in a certain way. I want you to write it like you would write a formula. So here's my nitrogen, here's my oxygen. I'm going to write these mole values as little subscripts. I have 1.85 moles of nitrogen and I have 4.63 moles of oxygen. It says divide all mole values by the smallest mole values. Nitrogen is the smallest mole value, so I'm going to divide everything by 1.85. And that will give me 1 here, and 4.63 divided by 1.05 gives me 2.5. Gives me 2.5. Okay, now it says if this does not give you a whole number, multiply all the values by a whole number that corresponds to your fractional subscript. So I have gotten a 0.5, okay? I have gotten a 0.5 here. So that means I have to multiply everything by 2, okay? So I have 1 nitrogen and I have 2.5 oxygen, must multiply by 2, must multiply by 2, and then I'm going to have 2 nitrogens and 5 oxygens. And this is my empirical formula. Okay, so what we did was we took the percentages and we made them into grams. Then we converted the grams into moles. Then we wrote the mole values next to the symbol for the element, like subscripts. We divided by the smallest whole number, which is step 3. Then because we got a fraction, we had to multiply it by a whole number in order to get a whole empirical formula that just has subscripts that are whole numbers. Okay, so let's do this again. Second problem. In a 100-gram sample of cinnamaldehyde, you have 81.79% carbon. So remember, percentages out of 100 can be directly translated into grams. So you have 81.79 grams of carbon. Then you have 6.10 grams of hydrogen. And you have 12.11 grams of oxygen. So this is going to be converted to moles and this is going to be converted to moles. Okay, so I'm going to do step 2. So percents have been turned into grams. Now let's convert grams of each element to moles of each element. So 1 mole of carbon on the top, molar mass of carbon on the bottom, then 1 mole of hydrogen on the top, molar mass of hydrogen on the bottom, then 1 mole of oxygen on the top, molar mass of oxygen on the bottom. Now let's convert. So I'm going to say grams of carbon cancel out. Okay, so that gives me 81.79 divided by 12.01 That'll give me 6.810 moles of carbon. And then grams of hydrogen cancel out. 6.10 divided by 1.01 gives me 6.04 moles of hydrogen. And then grams of oxygen cancel out. I have 0.7568 moles of oxygen. So step two, done. Okay. Step two, done. Okay, then it says divide all mole values by the smallest mole value. Like I said, I want you to write it like this. Okay, I want you to write carbon, hydrogen, oxygen. Then we're going to take these values, we're going to write it 6.810, 6.04, 0.7568. Then the smallest mole number is clearly the one for oxygen, so divide all of the values by 0.7568. 0.7568. Divide by 0.7568. This is going to be equal to 1. This is going to be equal to 7.98. And this is going to be equal to 8.998. Okay, this is equal to 8.998. So you have 8.998 carbon, 7.98 hydrogen, and 1 oxygen. Now we've done step number 3. Look at step number 4. Only if it's 0.5, 0.33, or 0.25, you have to multiply by 2, 3, or 4. 8.998 can be rounded to C9. That's almost 9 carbon atoms, right? Very tiny difference. Then 7.98 can be rounded up to 8, and then oxygen is just 1. So there is the empirical formula for a compound that contains 81.79% carbon, 6.10% hydrogen, and 12.11% oxygen. Okay, so the simplest whole number ratio. We don't know what the formula really is. It's just the empirical formula, which represents that this compound has 9 carbons to 8 hydrogens to 1 oxygen.